Alright, 1.6, tangent lines, an instantaneous rate of change. Yesterday we said that the average rate of change corresponds to the slope of a secant line. So today, instantaneous rate of change corresponds to the slope of a tangent line. A tangent line, of course, being a line that touches a curve once and has the same slope as the curve at that point. Okay, that's key definition of a tangent line. Hopefully we're familiar with that. You have a little space for notes on the relationship between the slope of secants and the slope of a tangent. What you need to do is draw, not big, and maybe you want to do it on the right. I'm going to do it on the left. But basically you want to draw a curve. In this case, I'm going to draw a parabola of some sort. And I'm going to draw a secant line. And the line intersects the curve at point P and at point Q. All right. Notes. As point Q becomes close to our tangent point P, as point Q becomes closer to point P, the slope of PQ becomes closer, or in brackets, approaches the slope of the tangent at P. So if we could take point Q and move it down the curve closer and closer and closer to point P, the closer we get it to point P, the closer that the slope of that line becomes to the slope of the tangent at P. So if we were to draw a tangent at P, again, a tangent line is a line that touches the curve at one place and has the exact same slope as the curve at that place. All right, so if Q were to come down here, down here, down here, you could see our red line would also kind of swing along with it. And the closer we could get Q to P, the closer the red line would be to the black line. Yes, the slope would become more and more the same, approaching. Okay. Denoted using an arrow. So this is the word approaching. Approaches is denoted using an arrow. So as Q approaches P, the slope of PQ approaches the slope of, I'm just going to call it the tangent at P. Okay, in English, the slope of PQ approaches the slope of the tangent at P. As Q approaches P, the slope of PQ approaches the slope of the tangent at P. Okay, so the average rate of change, indicated by the slope of PQ, gets closer and closer and closer to the instantaneous rate of change, represented by the slope of the tangent at P. To say it that way, the way I just said it, the average rate of change approaches the instantaneous rate of change as Q approaches P. Okay, we don't have the necessary skills to get the exact instantaneous rate of change. So we use average rate of change and we try to get closer and closer and closer, as close as we can, to instantaneous rate of change. And we do that using two methods, okay? So example 1 is a description of those two methods. Number 1 is we use the slope of a secant, and the second method is we use 2 points. So we use the point P and another point. But here we go. You guys have two pictures here. One looks like, well, they both look the exact same because they're the same picture. But one looks like that, and the other one looks like that. That's not going to fit. All right. Let's say they look like that. Method 1. Use the slope of a secant. So here we have the graph. Sorry, go ahead.
Do we have a function to work with? Or?
Nope, just a picture for now. The graph shows the approximate distance traveled by a parachutist the first 5 seconds after jumping out of the helicopter. How fast was the parachutist traveling 2 seconds after jumping out of the helicopter? So he's not pulled his chute yet. How can you tell? Well, his speed is increasing. His distance is getting greater and greater and greater with every passing second. So here we go. We are going to find out how fast approximately the parachutist is traveling at 2 seconds. So what you're going to do is put your first dot at the point at 2 seconds. Okay, we're going to call that P. And we're going to figure out the coordinates of the point P. They are, after 2 seconds, this distance, he's fallen 20 meters. So we know that that's 2, 20. Okay? So our goal is to find the instantaneous rate of change at this point. But we don't know how to do that, so we're going to use the slope of a secant. So in order to do a secant, we're just going to select another point, okay? So we are going to mark point P at t equals 2. Time equals 2 seconds. Then we're going to choose another point on the curve. Let's take t equals 3. Call it Q, and you can see by your chart that it's at 3:45. And then you can draw a secant line through those points. Don't even really need to draw it. And then you can determine the slope of that secant line. Determine slope of PQ. Okay, and that's the same as yesterday. The slope of PQ is the change in distance over the change in time. The change in distance is 45 minus 20. Change in time is 3 minus 2. Therefore, we have a slope of 25, which can be interpreted as, so using the secant. Using the secant, the parachutist velocity after falling for 2 seconds is approximately 25 meters per second. Okay, using that method, if our goal was to find his speed at 2 seconds, and we actually used the average of between 2 and 3 seconds, is our approximation too high or too low?
It's too high because it gets faster at 3.
Because he's going even faster at 3, so our approximation is high.
I think a better
Okay.
approximation would have been if we did it at 1.5 and 2.5.
So another way to do it, which we don't really ever actually do, in this situation, you're right. If we picked something at 2.5 and then at 1.5, we'd be a lot closer. Okay. That is not the case when you are dealing with a function with like lots of curves.
Yeah.
You always use the point that you're concerned with and then try to get closer and closer and closer to that point. Now, we could have also done better by, instead of using 2 and 3, why not use 2 and 2.1?
Well, we don't have a function, so.
Right. So we don't have a function to work with in this case. But when we do, we can, that's our strategy. You can use 2, 2.1, you can use 2.001, then you'd be getting really close.
Also, you probably get like 0 after rounding errors.
Yeah. Okay. Second method. I'm going to clear this.
You didn't actually do this one. But whatever. No.
Method number 2 is going to be use 2 points. Use 2 points on an approximate tangent line. Use 2 points on an approximate tangent line. So basically, we're going to take that same curve that we have, and we're going to indicate point P, which was 220. So your picture should look very much the same already. We're going to mark point P at 220. But then what we're going to do is actually select, we're going to draw, what we think looks like the tangent line at P. Okay, so we're going to draw approximate tangent line.
Tangent line looks like it has a slope of 1. So I guess 2.
Okay, so whatever yours looks like, make sure you have a straight line that looks like it has the same slope as the curve at that point. Okay, what's a good way to do that? Well, you can kind of see how it wedges out here. It should do that very similarly on both sides. Okay, so there is our approximate tangent line. And then the third thing we're going to do is pick a point along that tangent line. So your approximate tangent line likely goes through the point 340, or at least really close to it, depending on your sketch. Anyway, you don't have to use 340. Whichever point you can identify on your tangent line, any point, this will work. Okay, so choose a point, a second point on the tangent line. Choose a second point on the tangent line, and then find the slope of that approximate tangent line by using delta d, the change in distance, over the change in time. In this case, we have 40 minus 20 for our distance, and 3 minus 2 for our time. We end up with 20 over 1, which is 20. So using the approx tangent, the parachutist speed is 20 meters per second. And that's still approximately.
It's definitely more accurate though.
More accurate, yes. Okay. Okay, in the two methods that we used, which was using the secant line or using an approximate tangent line, either way, it's an approximation. Okay, whether one is closer than the other, they're both still approximations of the instantaneous rate of change because they either depend on the tangent line. I mean, obviously it goes through two different points on the curve. So there's an approximation. This method with the red line is determined by the skill of your hand in drawing an accurate tangent line and the accuracy of the second point that is on that line. Okay, so both of them are approximations. But also in both methods, the closer our second point is to point P, the more accurate we can be. In example 2, we're going to look at the exact same situation. This time we are given the table of values. So you're given a table of values that shows the distance of the parachutist recorded in half-second intervals. And so we're going to use that to estimate the parachutist's velocity at 2 seconds. And again, there's two points that you could choose. So you're always going to start with the point of interest. So you're going to start with point P, which is 220. And then you're going to select the point or the ordered pair that is closest to t equals 2. So let's pick t equals 2.5. Call that one Q. And we see the ordered pair 2.5, 31.25. And from there, we can get our average rate of change, which is simply the change in D over the change in T. Plug in what we know. The distance changes from 31.25 minus 20. And in the denominator, we've got 2.5 minus 2.0. We can reduce that to 11.25 over 0.5, which is the same as 11.25 times 2, which gives us 22.25. And I'm just going to right away go meters per second. Well, that's a pretty good approximation, a little bit closer than when we had the point t equals 2 and t equals 3. Is this approximation high or low?
What would low be?
Is it higher than reality or lower than reality for the parachutist speed at 2 seconds after jumping?
It's probably high.
It's still too high, right? Because we took the interval from 2 to 2.5.
Okay. So because we took 0.5.
Yeah. Note. Could also use the point at 1.5 seconds, which would be 1.5, comma 11.25. Okay, that would be another option for the next closest point. We chose to use the point just above at 2.5, but we could have used the point just below at 1.5. Good, again, still an approximation. Example 3, this time we're going to get closer and closer and closer and closer. We're going to bring Q closer and closer to point P because we have the function that models the approximate distance traveled by the parachutist. So in example 3, we're told that d of t is 5t squared. And we're going to work through this one fairly quickly through this chart, but we're going to fill in that chart, even though it's a bit tedious, just to give us an idea of what's going on here and how we can get closer and closer and closer to the real thing. So first of all, the first interval that we're going to take is t between 2 and 3 seconds after the parachutist jumps. So here we're getting an approximate rate of change over an interval of 1 full second. Okay, so now we're going to use the function that's given in order to find the change in distance in the first column. So you've got change in distance up here. You already have that. Basically, we already know the distance that he is at 2 seconds. We know that it is 20 meters. But we'll sub in, here's what we're going to do. We get the change when, the distance when t is 3, and we're going to subtract from the distance when t is 2. So this is what we're finding out. This is the change in distance from 1 over this interval. And then we just sub in what we know. So our function is 5t squared. So we've got 5 times 3 squared minus 5 times 2 squared. 3 squared is 9 times 5 is 45. 2 squared is 4 times 5 is 20. That gives us that the change in distance is 25 meters. Next column, the change in time is just your 3 minus 2. It's a 1 second interval. And then in your last column, we actually find the slope of this thing. We find the average rate of change, 25 over 1, which is just 25, and interpret it as meters per second. Okay, I'm going to skip down to the 2.1 interval. So leave the next boxes blank, go down to the third box and type t in the interval from 2 to 2.1. So t is greater than or equal to 2, less than or equal to 2.1. So now basically what we're doing is we're bringing point Q way closer to point P. And our answer is going to be more accurate. So our distance is going to be the distance at 2.1 minus the distance at 2. So we sub into our equation. We've got 5t squared. So we've got 5 times 2.1 squared minus 5 times 2 squared. 2.1 squared times 5 is 22.05. And we know this one is 20. So we end up with 2.05 as the distance that's traveled in this 0.1 second interval, a tenth of a second. Okay, change in time is just 2.1 minus 2, which is 0.1, which means your delta D over delta T is 2.05 over 0.1, which is just 2.05 times 10, which is 20.5. And if we want to interpret that right away, we're looking at a average speed in this interval of 20.5 meters per second. Now, that's getting pretty close to the real answer. Okay. Again, I'm going to skip the next box. No, let's do the next one and skip the last one. Okay, so we're going to bring Q even closer to P. We're going to use 2.01 as our interval.
Is this the fourth or fifth box?
This is the fourth box.
Right.
We're going to leave the fifth box empty because you can see what happens pretty easily after this one. You probably already do see it. So this time we're finding the distance traveled at 2.01 seconds and the difference between that and the distance having been traveled after 2 seconds. So we sub into our equation 2.01 everywhere we see t. And in our calculator, 2.01 squared times 5 is 20.2005. And we're going to subtract 20 from that, which leaves us with 0.2005. I think there's a typo here. Maybe not. Nope, looks good. And our interval here, I'm not going to do the math on it. It's an interval of 1/100th of a second, 0.01, which gives us a average rate of change over this interval of 0.2005 over 0.01, which is basically just our numerator times 100, which gives us 20.05 meters per second.
It would be fair to just say 20 because the more zeros we add to make it more accurate, the more 20.0000 and then ends with 5.
Yep, that's exactly right. So at this point, you would stop and say, okay, the average rate of change is approaching 20. Therefore, the velocity of the parachutist after 2 seconds is approximately 20 meters per second. So we'll say that now. The average ROC, rate of change, is approaching 20. Therefore, the velocity of the parachutist, after 2 seconds is approximately 20 meters per second. And again, we could have done this exercise with the interval, from 2 to 1, and then 2 to 1.9, 2 to 1.99. We could have picked values less than 2 to create our interval instead of values greater than 2.
Are we gonna ever use
Your practice problems are indicated there on the bottom of the page, page 71, numbers 1 through 5, 7 through 10. Again, you're responsible for knowing how to do those problems and problems like that.